aerospace and defense manufacturing,
machines and automation,
additive manufacturing,
smart manufacturing,
global manufacturing economy.
Welcome to Advanced Manufacturing Now, the podcast for manufacturing professionals, powered by SME. From the design screen to the shop floor to final assembly, we drive the conversation about making manufacturing smarter by connecting people who are passionate about manufacturing. Visit us at sme.org.
Hello, and welcome to Advanced Manufacturing Now, the podcast for manufacturing professionals. I'm Chris Mayhart, Managing Editor at SME Media, and your host today. We're joined by Robert McKiernan, VP of Strategic Sourcing and Advanced Manufacturing at Upwing Energy. Upwing Energy is a leading gas tech innovator and service company, an offshoot of Calnetics Technologies. Upwing was formed to focus on the production of hydrocarbons by providing a comprehensive end-to-end natural gas service enabled by their subsurface compressor systems. Robert has 30 years of global experience in new product development, manufacturing, production rollout, and operations, and has a proven track record in startup companies. As a global engineering leader, he has consistently demonstrated the ability to identify innovative solutions and apply analytical approaches to overcoming challenges and foster technology. Before joining Upwing, he served as president of HK Microturbine Corporation, where he played an integral role in technology development and product commercialization. Prior to that, he worked at Capstone Turbine Corporation, spending the majority of his tenure prototyping and commercializing Capstone's products while holding a variety of engineering, director, and management roles. He is the author of multiple U.S. utility patents and holds a B.S. in mechanical engineering from Loyola Marymount University. We're going to be talking about design and manufacturing for harsh environments and how additive manufacturing is enabling new design opportunities not available with traditional methods. Thanks for joining us, Robert. We're lucky to have you with us, and welcome to the show.
Thank you, Chris, for the introduction, and I'm excited to be able to provide some insight on the additive manufacturing that we're doing here at Upwing, which is truly an innovative technology that we're developing.
To help kick us off, for those of our listeners who may not be as familiar about the natural gas industry and extraction, I know Upwing Energy has developed a new subsurface compressor system, or SCS. Can you explain a little bit about what that system is and the benefits that Upwing's device brings?
Absolutely, Chris. So the compressor system, as we call it, a subsurface compressor system, an SCS, it's a high-speed downhole compressor that increases gas production and recoverable reserves by decreasing the bottom hole flowing pressure and causing a higher reserve drawdown. And what we do with this, kind of give a little bit of simplified view, is it's, to help understand it, it acts kind of as a straw pulling on gas out of the reservoir, and it can be visualized as a vacuum being placed within the well down at the gas well reservoir itself. And the way this happens is we have a device that's about 13 feet long. We drop it down into the gas well somewhere around 10,000 feet, but that level may change depending on where the reservoir is. And once that unit is deployed into the gas well, it increases the overall profitability and energy security by sustaining the natural gas production. So if you got wells that are aging and the gas production is minimal, by dropping our tool down into the gas well, it'll help increase that, and we can actually see a increase in gas production of over 200%, and also recoverability of 70% in the overall production by decreasing the bottom hole flow pressure and causing a higher reservoir drawdown. So clients can expect the incremental income ranging from anywhere to $200K to over $2 million per month based upon the specifics of the well.
I'm sure that's definitely a huge benefit for them, especially if you think about being able to extract more natural gas from an existing well. It might reduce the number of net new wells that need to be drilled.
Absolutely. And then it also means that there's less need of drilling new wells and fracking. So it overall lowers the emissions intensity of extracting process through its design and operating mechanics. So finally, the SCS replaces traditional surface wellhead compressors, which leak methane quite a bit. So again, we're really a green technology that we're introducing into increasing gas well production.
So, can you explain some of the challenges that come with designing and manufacturing equipment that's used in harsh environments such as oil and gas?
Yeah, Chris. So one of the biggest challenge with that is dealing with the corrosive environment that you're exposed to in a gas well. And primarily the worst part of it is the hydrogen disulfide and the percentage of that can exist in a gas well, along with the chlorides. And depending on the intensity of that, it can quickly shorten the life of a product. So we are really trying to work with materials that are not as susceptible to that corrosive environment.
So, is that one of the main approaches for overcoming these challenges? Is really the use of different material compositions and different material sciences?
That is correct.
So, I know I mentioned you guys have a newer subsurface compressor systems, the SCS, and you utilized additive manufacturing for the core compressor component. What additive technology did you utilize for that?
We use powder bed laser fusion for the production of our parts through additive manufacturing.
And what guided the decision-making process to utilize additive technology in that core compressor component?
So there's several different ways we could produce our parts. And initially we were producing those using wrought or billet nickel-based alloys, such that we would have to do a lot of subtractive manufacturing to get to the net shape. So as our technologies advanced, we looked at, can we continually use traditional, manufacturing methods to machine the parts out of billet stock, or could we look at investment casting, or what other options could we explore? Which then additive manufacturing presented a swim lane for us to further assess. And within that, we did a trade-off decision matrix looking at the different pros and cons of staying with traditional manufacturing from producing parts from billet versus investment cast, where you could go to near net and then machine what features you needed to do. Or, could we explore what additive manufacturing could provide us as an alternative approach?
So, did you run into any new challenges that came from utilizing additive manufacturing for these components?
I'd say the new challenge was really starting to understand the process and what was involved in getting from a concept all the way through a finished part. And really getting an understanding is, can we achieve the same material properties that we would be able to get out of a billet piece of material that yields a net component?
How did additive manufacturing help you overcome some of the challenges that's faced in designing and manufacturing equipment for use in harsh environments?
So for us to manage some of those harsh environments, we have to provide some special porting and instrumentation that allows us to be able to monitor the health and provide a lubrication to key areas in the product, such that it will manage itself well in these harsh environments. And traditionally, what we're having to do is doing a lot of cross drill feed holes within traditional machine methods and putting a lead plug in. But the additive manufacturing has allowed us to incorporate really intricate features within the parts such that we can directly provide the necessary design requirements to provide, whether it's a special feed for a particular location in the part or unique instrumentation that was not easily done through, say, CNC machined components out of billet or rod stock.
That's a great thing to think about, and being able to really develop those lubrication channels. I know I've talked with some mold makers who work in plastic extrusion mold making, and they found really a sort of similar concept in developing molds using additive manufacturing, that they could create much more complex and more effective cooling channels. So it's interesting to think of that same concept being used for lubrication.
Yes, and additionally, as our product, the compressor and the product itself has to be designed specific for each gas well. And so let's say I have a compressor configuration for a well that we're going to call well A, and then I've got a well B. Now, the compressor aerodynamic configuration for well B could be completely different than what would be required for well A. And with that being said, you could just imagine the effort it would take to machine components out of a wrought billet stock or even investment cash. You'd have to come up with unique castable definition each time or unique CNC programs to find your arrow blade geometry, where the additive manufacturing, we're able to take and generate that geometry within our design and CAD tools and directly upload that into the additive manufacturing software and quickly yield a part. And that in itself also has been a big advantage to where it's opened up to us the ability to be much more reactive in a positive way, to be able to yield parts very quickly versus looking at ways in a conventional manner.
So really designing for additive manufacturing takes a bit of a different thought process than traditional subtractive manufacturing. Did you guys run into any challenges with your engineers and designers as you were perhaps starting to think more about design for additive manufacturing versus what process needed to go into designing when you were doing subtractive?
Yeah, that's a really good question, Chris. Some of the challenges we do run into is that the engineers, they're sitting behind a CAD system, and this is in no way discounting their technical ability, but I think CAD has a tendency to provide a little bit of false sense of producibility. It's like, well, if I can generate it in the CAD system, we can produce it and walk through a real part. And what additive manufacturing has done is it's like, well, if I can grow the part, I can grow anything I want. But still, there need to be some considerations made like, okay, great, I got this really unique growing part. Am I able to, be able to post-process it without having any defects or deficiencies with it? And then more importantly, am I able to do the necessary subtractive manufacturing on that part to yield a finished part that'll support the requirements? And that, I think, in itself is trying to get the engineers to realize, hey, even though I can design this real cool part and I can grow it through additive manufacturing, I still need to take into consideration good design for manufacturing capabilities of what the processes can or cannot do.
So you've mentioned post-processing. How did you handle post-processing for your parts that you additive manufactured?
So that's really good. That was a little bit of a learning curve for us. We didn't have a full understanding of what was required when you were producing a part. And with what we understood is that, you generate the part from the additive manufacturing, it's put on a build plate. Okay, how do you get it off the build plate? And then from there, do we have to do a HIP process? And do we have to do any kind of solution age or stress relief? And then is there any kind of residual stress that we need to address depending on when the part's removed out the build plate? So we had to go through and really understanding each one of those steps. And some of those processes can add a lot of time to what you're doing, whereas you can, if you're buying wrought stock, you can get it in let's say, for example, we use a lot of Inconel 718. You can get that in the AMS 5663 form, which is solution aged, whereas for us, in additive manufacturing, you're getting, in essence, a semi-annealed part. If you want to solution age it, you got to go out for that solution age process, so part of the finalization of the material through its overall, manufacturing process procedures.
As you guys continue to think about, new products or improving the existing designs, do you see more opportunities with additive technology and the ability to customize that material chemistry that can then further help support longevity for your products?
So not so much right now on looking how the material chemistry can be augmented. However, we are working with a supplier that provides a post-processing that will increase the case hardness of the material from where you would have, let's say, a Rockwell C of 45. Can we get up to a Rockwell C of 75, which would further improve some of the components within the SCS, their operable life?
Where do you see additive manufacturing going next, or even what do you see as some of those limitations that need to be overcome to get to that next stage of the technology?
I think for us, we do our compressor on the subsurface unit can be made up of several stages of an axial flow compressor, and the aerogeometry is really critical. And depending on the attack angle of the compressor blades or the stator blades can be somewhat of a limiting factor of what you can produce without the parts starting to deform through the printing process. And I think that's really an area that additive manufacturing could work on is one, how can we take and manage certain feature definition that may not be relatively available to do today? How can we do it slightly differently? I don't know if it's maybe if you can control the laser intensity as you're sintering the powder, or maybe a different way to do the support structures. But that is a bit of a consideration that we need to take as we're producing our parts where things could be better. Also, I think within the overall post-processing to where, if I take the part off the build plate, I got to go through HIP and the solution age and then, cut it off the build plate. That in itself is a lengthy process, just working with the various suppliers and handoffs. Can something be done differently in that? I think also the material availability within additive manufacturing, I want to say that maybe I think there's less than 10 different materials that can be used currently today, but it may be slightly more than that from last time I checked. But I think different kind of alloys, and like you brought up earlier, is there a way to do kind of a custom blend of alloys to get more of a material property you want? Also, I think print time, can they improve print time? I know that, some suppliers have more than one laser on their system to where they can be a little bit more aggressive on the print. Also, as AI becomes more prevalent within today's world, is there a way to generate some AI into this additive manufacturing? I know we've produced some parts. The parts have failed in the printing process, and you would ask yourself, well, how come the software is unable to pick this up in advance to where now I got to scrap out the build? So those are kind of some things that come to mind.
Sure. And I imagine, I will be honest, I am not the foremost authority on oil and gas, but I can certainly see it as being an industry where there's a fair number of standards and certifications that you're looking for due to the complexity and harsh environment. Did you run into any challenges in that space utilizing additive versus a traditional machining?
Not at the moment. I mean, we do try to follow the American Petroleum Institute for additive manufacturing metallic components. It's their API standard 20S. We use that a little bit as a benchmark for us to help understand what we need to do. And you bring up a really good point within that, Chris, is that because additive is somewhat new, there are some testing that we do with what we have done just to kind of prove to ourselves that we are getting the necessary material properties to meet our application requirements.
What do you see as sort of the next step for Upwing Energy?
For Upwing, it's really transitioning as we go through our pre-commercialization, development, and understanding our application in the wells, is to further commercialize a product. And within that, we look at the overall, what is the best way to produce our parts and what makes sense. I mean, for example, maybe what I'm doing today in additive manufacturing, because we are doing so many incremental changes and we're able to get a quick result on what we're doing. Maybe some of those parts would convert to investment cast because now it's a standardized component within the system. And I would then be selective as to what form of manufacturing processes I want to consider as the technology matures.
Well, Robert, I want to thank you for taking time out of your day to join us. It's certainly been an interesting and engaging conversation. If listeners want to learn more about Upwing Energy, where should they go?
Our website, it's upwingenergy.com, and there's a lot of good information there to further understand the technology and the innovative approaches that Upwing is taking. So, Chris, thank you for this opportunity to do this podcast with you, and hopefully we can do this again sometime in the future.
Been my pleasure, and I hope so. And to stay up to date about what's happening in manufacturing today and hear more podcasts, visit us at sme.org.